Hello guys, welcome back. Today I'm gonna carry on a little bit about um, the hydrogen atom. So hydrogen atom, and so we saw uh, how the electron around the nucleus, which was just a proton, would behave, and we know that it's a fuzzy um, probability distribution where you can find your electron rather than an orbit. But let's assume that we focus on one position only. We can still think about this as a mean value around some radius, which we can think about it as fixed, an average distance between the radius and the distance. And when I want to talk about this a bit more in detail is what happens when this, by the way, this electron has an energy, mean energy, kinetic energy and potential energy, and is roughly 1 mv square plus or minus, never remember, plus 1 over r square plus some constant and the q and the charge. And this is the distance to the radius, and this is the kinetic energy. Okay, so but suppose what happens if you if you if you promote the energy of this electron with some light. Suppose you shine some light inside in the system, and then it gets absorbed by the electron, and this electron gets plus some extra energy from the light. What happens to the electron? Where do the electron go? Okay, and this is one thing that I would like to touch upon. And the other thing is to show you a bit of what's behind when you have more electrons. Suppose you have a helium atom at the moment, not hydrogen but helium. So two protons. Therefore, you can host two electrons in order to have um, your neutral balance between the charges, because we know that an atom will have mean. Oops, sorry guys. This is the video. It's a bit shaky. Because you know that the atom will have a mean charge. Oh, sorry. Yes. So you mean charge of 0, net charge of 0, because there are two pluses and two minuses. Otherwise, you will have an ion. Okay. And to see what happens when you talk about this, we need to talk about Pauli exclusion principle. Pauli exclusion principle, and then spin. Okay, so I will try to go through all of these ideas, and but first I want to give you, and then there will be a simple animation about different orbitals in atoms. So just to remind something of that you might be familiar with is in chemistry, when you have many electrons or yeah, anyway, some configuration, you can have orbitals around the nucleus. Your electron will be moving in different configuration. And the first one that we saw, it was like a spherical distribution around around the nucleus. But if you give more energy, as I said, what could be happening is that your electron, due to this extra energy, will start to populate this area as well. So will be a larger sphere distribution, spheric distribution. And this is one thing that could happen. But there are other things that could happen. For example, it could be that the energy is given in such a way that the shape of the orbit that the electron would follow would be something like this. I will show you in a sec, which is two lobes around around the nucleus. Okay, two lobes. You don't know where it is, but it could be somewhere here. And this is a different way of, and your electron could be in one of those areas. And these are called fancy names, but for example, S and P orbitals. S is spherical, P is this two lobe shaped orbital. But and what is different between these two orbital is the angular momentum, for example, and the energy. Angular momentum. We talked about angular momentum in another video, and maybe we will talk about it more in the future. But basically, it's the way the angular distribution is shaped. Okay, so why? So one thing is this different distribution that is due to the energy that you give. But now suppose and so there are two things we need to consider. Suppose now you have a instead of a hydrogen atom, you have a helium atom. So you put two protons with no neutrons. So there are two charges. And where can you put your electrons? Where can they be? The idea is that by the exclusion Pauli principle, exclusion principle, there might be a C there, exclusion, never remember how to write it, this one. Pauli principle, let's say. Sorry. Pauli principle. Two electrons cannot have the same state. Okay? So electron 1 is psi 1 is different. This is the state, the quantum state. Okay? State. So the distribution of your electron must be different from psi 2 in some way. In some way, they has to be different. For example, it could be the blue one is one, and the green one is the other because there's a different radius, so different energy. That's fine. The blue and the orange one, they have different angular momentum, so that's fine. And actually, you could put them two in the blue one eventually, if you want. How in the lowest energy level there are two electrons that you can put, and you might argue why you can put two electrons in the same shape, in the same state, because there is one particularity about the electron that we need to always remember, which is called spin, which is a property of the electron, and that is a way of interacting with the electron with the magnetic field. Okay, so it's so this is a bit I will skip loads of detail here. I will just give you a quick idea. If you have a current circuiting in a circle, there is a magnetic field that is pointing up this way. This is called Biot-Savart law or Ampere law, one of the two. I will give a link in the details. But basically you have a current and you have a magnetic field that is sticking out. And the magnetic field can be pointing up or down. And they will have different energy level in presence of magnetic fields. The spin is somehow similar to this, is as if the current in the particle is giving rise to a quantity that is called the spin, that is either up or down, and interacts with the magnetic field, external magnetic field B. It's not as it's similar to a current that is circulating around an axis, but there is no current circulating. It's just a particle. It's just a characteristic of the particle called spin, and differentiate the particles into main groups, which are called, which is important to know, bosons and fermions. And depending if the spin is 0, 1, 2, 3, or 1/2, 3/2, 5/2, so it's an integer or half integer, okay? And the electron a spin is 1/2, so it's a fermion. And for example, the photon, the particle of light, spin 1, which is a boson. Okay. There are lots of differences between bosons and fermions. One main difference is that fermions do not like to stay with each other, so they try to, and this is in fact at the heart of the Pauli exclusion principle, is that fermions do not like to be in the same place. While bosons, as we saw last time with laser light, you can have as many photons as you want in a laser beam. In a very narrow beam, you can have many photons of the same kind, and they like to bunch with each other. Fermions don't. And in fact, we can have two electrons in the lowest energy level, one with spin up and the other with spin down. They will have a slightly different, the state will be different because the spin is different, so there will be two different complex number, and in fact there will be orthogonal complex number, okay, meaning that psi1 times psi2 is 0, orthogonal, meaning that they don't share any, they don't have anything in common. Orthogonal is like when you have your reference frame system x, y, and z, the axis of your cube, they are orthogonal 90 degrees. They don't share anything in common. You can project, and you cannot project one on top of the other. So orthogonal meaning that they are different in the best way, and when one is spin up and the other is spin down, they will be orthogonal, so they can be in the same ground state of your electron, of your atom, sorry. One thing that I want to just quickly tell you about as well is that orthogonal is also a characteristic of these orbitals that we see. The green one, the blue one, and the orange one, they are all orthogonal, meaning that somehow the product is 0. And you can think about this. They're not just vectors; they're functions. But you can kind of see functions which are orthogonal. Think about the sinusoid, which is like this, and the cosinusoid, which is like this. If you do the product of the two, you will see that they have, or even take something easier. Sorry, even easier than that. Suppose we have this function here, which are square waves. And then suppose we have this other function, which is 0 here, 1 here, 0 here, 1 here, and 0 here. As you can see, where one is 0, the other is 1, and the other one is 0. So it's easy to see that f1 of x times g of x, if we call them like this, will be 0. And even the integral will be 0 because it's just the sum of all the multiplication of the two. So you can kind of think function which are orthogonal in the way that they don't get in each other's way. So where one is 0, the other is not, or something like that. It's way more complicated than that. But the idea is that they don't get in each other ways, and they can be with each other at the same time because they don't occupy the same space. Okay, so this is to say that thanks to spin and Pauli exclusion principle, this electron will populate the atoms, and if you want to stick another electron inside, and for example think about the lithium atom, you cannot put it in the lowest energy state. It will be in another one, a different one, either here or there, because there is no more space in the state space in the overground state, because you have two spin, one up and one down, and the shape of the electron is already settled by the sphere, the blue sphere. And this is how, by the way, how matters grows, because you cannot stick all the electrons in the lowest energy, and they will start to separate in distance, and therefore you have matter, actual physical objects, which are expanded in space, because electrons repels each other fundamentally, not only because of their charge, but also because of the exclusion principle. Okay, so I hope I didn't confuse you too much. What we discussed about is the Pauli principle, exclusion principle, that says that two electrons cannot be in the same state. Okay. We saw that spin is a properties that interact with the magnetic field, and it differentiates fermions and bosons. Fermions like to be separated, so they create matters as expanded matters that we know it. Bosons like to stick to each other, and they create, for example, what is called condensed matter, or even light. By that matter, is condensed matter if you want. There are particles of light that are bunched together in the same state. And the spin is that thing that allows us to populate atoms in this way. And we talk about orbitals, meaning that orbitals are the shape of the wave functions, spatial wave function, depending on the radial distribution and angular distribution. Angular distribution. Which are different between different energy level, and these are populated when you excite your electron to higher energy level, or you put more electron in the same atoms to create other atoms. And then finally we discuss a little bit about orthogonality, meaning that the product of two states is zero, meaning and this can be vectors or functions, it doesn't matter. This is the product of two vector or two function is zero, meaning that they can coexist together because they don't occupy the same space, they don't overlap much between each other. And this is an example of that I draw in this picture. And the other example was the spin plus 1/2 and minus 1/2 is enough to create two states which are different, as I said before. Okay, so next there will be a video to show you the orbitals. I hope you like this one. It was a brief one. We will talk about more stuff, but I hope it was clear and interesting. Okay, see you next time. Bye.